This video will help you with assigning formal charges in a molecule or ion, why we do it, and how we do it. First, let's distinguish between formal charge and oxidation number. You may be familiar with assigning oxidation numbers in compounds and ions. It's a bookkeeping method that gives the more electronegative atom all the electrons as if the compound would be ionic. There may be no reality behind the oxidation number, but it is a useful accounting technique. So let's look at chromium and the dichromate ion on the right. Oxygen is always assigned a -2 unless it's peroxide, and this is not a peroxide. There are 7 oxygens, so 7 times -2 is -14. However, the overall ion has a charge of -2, so that's going to be left over after we neutralize the other 6 oxygen -2s. Only 12 of the negative charges are neutralized, and there are 2 chromiums to do it, so each chromium is assigned a +6 oxidation number. Assigning oxidation numbers is an important skill, but it has little or nothing to do with assigning formal charges in compounds that are definitely covalently bonded. Why do we assign formal charges? Well, they help us draw Lewis electron dot diagrams for molecules, and they help us determine which of the Lewis structures, if we have several possible ones, would have the lowest energy. The lowest energy structure is the one that is preferred to use whenever you're diagramming a chemical reaction. So let's do one. Ozone, the second allotrope of oxygen, is O3. This is what it looks like. It is a bent molecule. Now, each oxygen has 6 valence electrons, or 18 between the 3 valence electrons. So the Lewis rules are applied. We make 2 sigma bonds between the central oxygen and the 2 oxygens on the wings. There are 2 electrons left, so we make a double bond between 2 of the oxygens. That would, of course, be a pi bond. We could have put the double bond on the other side of the molecule. There's really no reason why we put it on the left. It could just as easily look like that. Now, let's assign formal charges. The formula is seen here. The formal charge is equal to the number of valence electrons subtracting the non-bonded electrons, and then half of the bonded electrons that are shared with other atoms. So we'll do that. The formal charge for the left-hand oxygen is as follows. 6 valence electrons for oxygen. We subtract 4, as you can see, these 2 lone pairs here. And then we subtract half of the bonded electrons. Well, there are 4 bonded electrons here in the double bond. Half of that, of course, is 2. So 6 minus 4 minus 2 is 0. The formal charge on the left-hand oxygen is 0. Let's do the central oxygen. 6 valence electrons for oxygen. Now we subtract 2 because there's only 1 lone pair. And then we subtract 1, 2, 3 bonds, so 6 electrons that are bonded. Divide that by 2 and we get a +1. The formal charge on the central oxygen is +1. And finally, let's do the right-hand oxygen. 6 total valence electrons, and there are 6 electrons here in the 3 lone pairs. We then subtract half of the 2 electrons in the bond, and we get overall a -1 formal charge on the right oxygen. Now we can assign formal charges to the other resonance structure to see if one's lower energy than the other. You may see that this is a mirror image of the one we just worked on, we could redo the numbers, but it's pretty easy. We just do it backwards. So the formal charge is reverse. And now on the left hand we have the -1, in the middle still a +1, and on the right we have the 0. What does the exercise tell us about the energies of the two different resonance structures? It tells us that the central oxygen formal charge doesn't change. It's always +1. The other two oxygens just swap formal charges. So the energies of both resonance structures are exactly the same, and neither one is going to be preferred. Now, how can we use formal charge to choose a structure if we have two possibles? Well, let's do an easy one. Formal charge assignments can help us choose the best one. Now, first, the formal charges on each atom should be equal to or close to 0. And formal charge separation should be minimized, and of course the overall molecule should have a 0, or if it's an ion, it should have a total charge equal to the ionic charge. Let's use formaldehyde as an example. Its formula is CH2O. By the way, it is not actually a carbohydrate. There are two possible arrangements. Because hydrogen only bonds once, it must be the terminal atom in a structure. So there's one way, and there's the other way. We put the oxygen down. Here are the Lewis structures for that possible. We had 12 electrons. And we're going to give both carbon and oxygen an octet. There's the first one. And that looks interesting, but it also looks strange, because you see the oxygen here is bonded, a double bond to the carbon and a single bond to the hydrogen. That's 3 bonds. That's very strange. Here's the second one. Let's do, and of course there's 2 lone pairs up here on top of the second one. So let's assign formal charges using the method we already have used. The left-hand molecule, both hydrogen atoms are 1 valence electron. There are no lone pairs. So subtract 0, and then we have 1 bond, so 2 over 2 is 1. 1 minus 1 is 0, both for the hydrogens. The carbon, which has 4 valence electrons, we subtract the lone pair, 2 here, and it's got 3 bonds, so 6 electrons. We divide that by 2. 4 minus 2 minus 3 is a -1. We look at the oxygen, we see likewise, starts off with 6 valence electrons, subtract 2 for the lone pair, and it has 3 bonds, so 6 divided by 2 is 3. 6 minus 2 minus 3 is +1. The overall molecule charge is 0, but we have a +1 charge on oxygen, which is definitely more electronegative and ought to get the electrons. And we have a separation of charges. So that's got an energy problem. Now let's look at the other one. And we've put in the 2 lone pairs. We assign formal charges as before. This right-hand molecule, both hydrogen atoms are 1 electron minus no lone pairs, minus 1 bond, so 2 electrons over 2. 1 minus 1 is 0. The carbon has 4 valence electrons. There are no lone pairs, and we subtract half of the 8 electrons in the 4 bonds, and we get, again, a 0. And finally, we do the oxygen. 6 valence electrons. We've got 4 of them in lone pairs, so we subtract those. And then we've got 4 of them in the 2 double bonds, in the 2 single bonds, or a sigma and a pi. So that double bond takes 2 more away. So 6 minus 4 minus 2 is also 0. The overall molecule charge is 0, as is the one on the left. But we have no charge separation because we don't have any formal charges on any of the atoms. And oxygen doesn't have the weird +1 charge we do in the molecule on the left. So, if we use the formal charge method, we find that the lower energy molecule must be the one on the right, and that will be the preferred configuration. We will never see formaldehyde showing the formula with a double bond between the carbon and oxygen in the middle.